Hey girls, I have a feeling this is frozen. All right. Hey girls, one of you had a question about example 6.7 in the book, and I wanted to go ahead and cover it because it had a lot to do with the laboratory that we did a couple of days ago with the calorimetry. So I wanted to kind of drive home a point. If you have something reacting in water, pretend that looks like water, okay? Here, we'll make it blue. See, there, you blue water, okay? So we have something reacting in water. Like in this example, it says lead, and the lead starts at like a high temperature, like 90 degrees Celsius or something. So I have PB, a big ball of lead, ka-chink, and it drops down into the water. And the initial temperature, so I'll put TI, for the lead was like 90 degrees Celsius. By the time this whole reaction was over, when you measure the temperature of the water, what you wind up getting is some value. In the example in the book, they said the final temperature of water was, I think, 22.5 degrees Celsius. 22.5 degrees Celsius. So, basically what you have here are you have two different sets of calculations. You can calculate with the formula that we used in class, Q equals MCAT. With this formula, you can calculate the heat evolved for water, QH2O, or you can calculate the heat evolved for the lead, PB equals MCAT. Okay? When it comes to the water, you have the mass of the water, you have the specific heat capacity of the water, and you have the change in temperature of the water. When it comes to the heat, as far as this little ball of lead is concerned, you have the mass of the ball of lead, you have the specific heat capacity for the ball of lead, and you have the change in temperature for the ball of lead. Now the really cool thing is, whatever heat, like let's say heat was given from one to the next, whoever absorbed the heat, he took it from someone, right? So in a reaction where water, for example, was absorbing heat, he's absorbing it from the person. Let's pretend lead is a person for a second. See, look, there's a little smiley face. Hi, and he has hair. Anyway, the person he took it from lost the exact same amount of heat that water gained. And if water lost heat, then water lost the exact same amount of heat that this little dude gained, okay? So this is what we did in the laboratory. We said that Q of water, and of course it was the water plus the calorimeter or whatever the apparatus is around it, but for the sake of our calculations, I'm just not going to write that, even though it'll probably get me fired. But anyway, so the heat of the water, the heat evolved of the water, is exactly the same as the heat evolved of the lead. The only difference is one of them gained and one of them lost. So I'm just going to put a negative value here. It doesn't matter which one I do. The point is, I'm trying to say that the heat evolved from one of them is the exact same amount as the other, but the opposite sign. Because in chemistry, when we say, for example, negative, we're saying losing heat. When we say positive, we're saying gaining heat. So anyway, if you understand this, then calculations like 6.7 should be easy to work out. So keeping this in mind now, I'm going to turn the page and we're going to get started with the example. Ooh, I just tore the page. Okay. What they give us in the example, actually here, I want to write it like this. What they give us in this example is they said, okay, we're going to give you a mass of the lead. So they gave us the mass of the lead. Mass of the lead is equal to, and I'm just rounding because I don't have, I mean, in your book it's like 47 grams. I'm just going to round it up to 27 grams because, yeah, I have here 26.5. It's becoming 27. We don't care. Anyway, and then I have they gave me the initial temperature of the lead. So I'm going to put T, a little I, pretend that looks like an I, and then the letters PB, just for my own knowledge. That's the initial temperature of the lead, 90 degrees Celsius, okay? That's that. And then on the other side, now they're also giving us the mass of the water, mass of H2O. They're telling me it's 100 milliliters. Now, for those of you who remember from the lab, when we're talking about water, 1 milliliter is equal to 1 gram. So 100 milliliters of water, if I want to calculate the mass, it's equal to 100 grams of water. And then they gave me the initial temperature of water. Oh, okay, it was 22.5 degrees Celsius, sorry. And then they gave me the final temperature of the water, which was 23 degrees Celsius. Okay, so if I have the final temperature of the water, does that mean that I also have the final temperature of the lead? Yes, it does. So at this point, I'm just going to start adding some stuff that I know based on what we just talked about. So I know, for example, that this final temperature of the water, because, you know, again, I have this reaction happening and blah, 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 blah. By the time the reaction is finished, I'm assuming that the temperature of the ball of lead inside the water is equal to the temperature of the water, because we talked about how heat is always going to travel down a gradient. So the final temperature, T final, for the lead is also equal to 23 degrees Celsius. And again, I'm rounding. I don't remember what the values are in the book, but I think it was like 23.17 or something. And then what else can I get? I think we also talked about in class, we have the specific heat capacity for water, C, H2O. You can look on a table and you can find that the specific heat capacity for water is around 4.2 joules per gram times degree Celsius. Okay, so I haven't even looked at what they wanted from me yet, but I'm just trying to show you everything that I can possibly get before I start with this. So now the next thing that I'm going to look at is, what do they want? In this question, they make you think backwards. They say you want the specific heat capacity, so I'm going to put the letter C for lead. That's what they actually want. And again, I've got two formulas here. I have Q of lead. I have the heat evolved from the lead, which is MCat, but it's the mass of the lead, times the specific heat capacity of the lead, times the change in temperature of the lead. And then I also have Q equals MCat when it comes to the water. The heat evolved for water, the mass of water, the specific heat of water, and the change in temperature of water, okay? So this is kind of like an SAT question for your math. I mean, you have two formulas, and what we said on the last page is that this guy is equal to this guy. These two values are equal to each other. So all I have to do is I have to set these formulas equal to each other. Or what I'm going to do on the next page is I'm going to say, no, you know what, I don't want to get confused with my variables. Can I find the change in heat, like the heat evolved for water? Do I have the mass? Do I have the specific heat of water? And do I have the change in temperature? Yes. So if I get this, then can I plug it in here? Now I'll have, if I just take the opposite, I'll take the negative of whatever I get, and I'll have the change in heat for lead. And they gave me the mass for lead. I can get the change in temperature for lead, and the only variable I'm left with that I have to solve for is C. So that's exactly what I'm doing. So I'm going to work it out on the next page. Actually, I'm going to tear that so I can actually look at it. I have, okay, I'm going to do Q, H2O. So I'm going to talk about the heat evolved for water, and it's equal to the mass of water, which we said was 100 grams, times the change in temperature of water. Now the change in temperature here is always the final temperature minus the initial temperature. So it's 23 degrees Celsius minus 22.5 is about 0.5 degrees Celsius. 0.5 degrees Celsius, okay, times the the heat capacity, the specific heat capacity for water. So I'm just going to say 4 joules per gram times degree Celsius because I'm just working on the procedure. I don't, you know. Okay, so what I'm going to wind up with is 400 divided by 2 is about 200. Okay, the reason why I was rounding was just so that I could do the math in my head. My grams cancel, my degrees Celsius cancel. I wind up with 200 joules. That is the first part of this problem. I just found that the heat evolved from the water was positive 200 joules, which means that the water absorbed 200 joules of heat in this reaction. Now, I know from the previous page that the heat that was absorbed from water, he had to have gotten it from someone, so he got it from the lead. So those 200 joules of water, if I convert it to negative 200 joules, now I'm talking about the value of the heat evolved for lead. Do you see how I made that parallel? Because the water has absorbed this heat from someone. The person he got it from is our little ball of lead. See, there, that's our lead guy. Okay, so it's the same value, but just a different sign, meaning that lead is losing the heat to water, who's gaining the heat. And now I'm ready to move on. I'm going right back here, and I can add to my givens, because what is the thing that I want? I want the specific heat capacity for lead. And they gave me, you know, if I want to use Q equals MCAT, it's perfect, I can, because I have the mass of the lead, I have the change in temperature of the lead, and now I have Q as well. So I'm going to say, okay, bismillah, where is it? Okay, so the change in heat for lead is equal to the mass of lead times the specific heat of lead, which is what I want to solve for, times the change in temperature of lead. Now, I always like to go ahead and do the algebra first and then just plug in my numbers. So I'm going to go ahead and divide both sides by M and change in temperature. Mass, PV, and change in temperature of the lead. Okay? I'm dividing both sides by this because I want to isolate the specific heat capacity for lead. Okay, so now I wind up with the specific heat capacity for lead, which is what they're asking me for, is equal to the heat that was lost by lead divided by the mass of lead times the change in temperature of lead. Okay, and now all I have to do is literally just plug in my numbers again, and the heat we said was negative 200 joules. I don't actually know how to turn that off because, wait. Anyway, the heat evolved in lead. I hope you can still hear me because I turned the volume way down. But anyway, the mass of lead, they said, was 27. You know what? It's becoming bigger and bigger. I'm changing it to 30. Now we have 30 grams of lead just because I said so. And anyway, the change in temperature of lead, it was 90 degrees Celsius minus 23. So what do you have? That would be 67 degrees, which I don't feel like doing in my head. So we're going to pretend that they actually told us it was 93 degrees Celsius because, yeah, now I have 30 times 70 degrees Celsius. I'm cheating and changing the numbers because I don't feel like doing the math in my head. But anyway, so this winds up becoming a negative 200 divided by 2100 joules per gram per degree Celsius, which is going to round, you know, kind of. Anyway, you guys worry about the math anyway. I was rounding because I thought it would make it easier. But anyway, as long as you see the procedure, again, going over it again, we had the lead and he was dropped in water, okay? So he was really hot, and then he got dropped in water, and then he cooled off. But how did he cool off? Because he gave his heat to the water, okay? So the first thing we calculated was how much heat the water absorbed, and then we were able to actually find the specific heat capacity for lead, which is going to be grossly exaggerated if you do my calculations, because I was just rounding arbitrarily the entire way through, which you're not going to do. But anyway, as long as you see the procedure. All right, I think that's it, so I'll see if there's any other examples. Bye, guys.